So moving on to step 6, let's talk about how we actually design an experiment and gather data. Now, normally you would design the experiment and then make your prediction based on the capabilities of the experiment. I talked about the prediction already because I like to talk about the hypothesis and prediction together, and I like to talk about the test and the data together. So really you would probably make your test and then predict and then do your test. But we're going to talk about it in a slightly different order. So as a review, you want a hypothesis that is rational based on your previous observations. And then you're going to make a prediction of the specific results that you expect that would support that hypothesis. And then you're going to conduct an experiment. Now, it is critically important that that experiment actually tests the question in the hypothesis that you're asking. So if we're thinking about this echinacea question, our hypothesis says that echinacea reduces the likelihood of catching the cold and the duration of the cold. So we have to test whether or not individuals were less likely to get a cold and whether or not that cold was longer than usual, shorter than usual. If it doesn't test those things, we're not actually testing our hypothesis. So you have to be really careful in the way that you design your experiment so that you're actually testing and answering the question that you want to test. So I put up our reminder of our prediction. If echinacea reduces the likelihood of catching the common cold and the durations of the symptoms, then individuals taking echinacea should get a cold less frequently, so there's some data, than those not taking it. And when they do get it, their illness should not last as long. So that's some more data. So the 2 points of data we're going to collect are whether or not the individual gets the cold less, individuals get the cold less frequently, and how long it actually lasts. So there are a lot of things that you need to keep in mind when you are doing an experiment. So we're going to talk about some of those things. First, I'm going to talk about what they actually did in this experiment. So we have a group of subjects. These are our test subjects, 437 of them, in fact. These are all volunteers. Now, if you're working with humans, you actually have to get approval and things like that for real studies. So they would have gone through this whole process of actually getting approval and these people signing consent forms and things like that. So then these individuals were broken up randomly, that's really important, into 4 groups. So 2 of those groups, groups 1 and 2, took echinacea tablets once a day, and 2 of them had no echinacea at all. So that's really important because one of these groups is going to act as, 2 of these groups are going to act as control groups. So the controls are sort of your comparison. They're the ones that get no treatment because you need a baseline. What is the duration of this cold? How likely are they to get it without taking anything? And then how does echinacea improve that cold? So of the people that, let me back up a little bit. These 2 groups were treated slightly different. The first 2 groups, groups 1 and 2, were used to test whether or not echinacea reduced their chances of getting a cold. So 1 week before exposure to the virus, one group was given echinacea and one group was given a placebo. So we'll talk about a placebo in a minute. A placebo is basically a fake treatment. So the individuals were told, if you're in one of these groups, you could be getting echinacea or you could be getting a tablet, sugar tablet or something. You won't know what it is, but some of you will be getting the treatment, some of you won't. That's one of their controls. Then everybody was exposed, all groups, and then groups 3 and 4 were given, were tested for the duration of the cold. So groups 1 and 2, they wanted to see if they were less likely to get the cold, and then groups 3 and 4 were there to test the duration. And in fact, all of them were kind of used to test the duration. So we've got, again, individuals in groups 3 and 4 that were given echinacea and some that were given a placebo. Groups 3 and 4 didn't start until after. So they're sort of testing also when is the best time, although that's not the specific question they were getting. So over here we've got a little explanation about how they were treated. They were given, groups 1 and 2 were given tablets for 7 days prior to exposure, while groups 3 and 4 were not. And then they all took their echinacea for 5 days after the initial exposure to see if symptoms were reduced. So let's talk about a little bit of vocabulary. This would be a fantastic time to bust out your favorite flashcards. All right, so the treatment is just whatever you're doing to those poor individuals that are being experimented upon. In this case, those receiving treatment are receiving echinacea. Those that receive the treatment are called the experimental group. So those are the ones that are actually getting the treatment. And then you have the control group. So this is your comparison group. They are or should be treated identically as much as possible to the experimental group. So I said over here that these individuals were given a placebo. Those are a control group. Because they are given a pill, but it doesn't contain echinacea. And so that sort of allows you to treat your control group as close to the same way as possible. So then there are variables. So these are basically the things that you're going to measure, the differences between your experimental group and your controlled group. So you have 2 types of variables, the independent, I don't have these written out. The independent and the dependent variable. So the independent variable is the one that you control. So in this case, the independent variable is whether or not they get the treatment. So you control if they get the treatment or not. And then the dependent variable is the data that you collect. So they get the treatment or they don't, what happens? That is your dependent variable. So independent variable is the thing that's the same. The treatment that you're given, it's given to everybody or it's not given to everybody. And then they react in a different way. That is your dependent variable. The controls in an experiment are the most important feature. If you just gave people echinacea, you'd have nothing to compare it to. It wouldn't be any different than meeting a lady at CVS who's like, yes, echinacea makes my cold shorter because I say so. But without having a control, you have nothing to compare that to. So if some people get echinacea and some people don't, you have this baseline to which you can compare your echinacea treatment. So you want to make the differences between your control and your experimental group as minimal as possible. As much as you can, you want them treated the same. So these individuals might have been, this study might have been done at a medical facility. And so maybe they asked these people to live at the medical facility for 2 weeks so they know what they're eating, they know their climate control, they know that they're getting rest, they know they're not stressed at work. That reduces all of those other outside variables that can affect those individuals, so that you know that any differences in your results are due to your treatment. Or if there are no differences, you know that everything else being equal, echinacea didn't help. So there's this fantastic example in your book of an experiment where no controls were used. So they several years ago, somebody did this study in an attempt to treat ulcers. So ulcers are basically holes in the lining of your stomach, and then because you have basically an open sore in your stomach and your stomach is acidic, it causes all kinds of pain and problems. And so somebody thought it would be a good idea to put a balloon into the stomach and fill it with cold fluid. I don't know why you would do this, but somebody thought that this would be great. And So they treated all of their individuals with ulcers, and all of them experienced relief. So it's really tempting in this situation to say, oh, look, it worked. It's fabulous. But you can't really say that because you didn't have anybody that you didn't perform this treatment on. So how do you know that that's the reason that it worked? You don't. So in a second experiment later, somebody said, hey, this experiment was flawed. They didn't use any control, so they redid it. And they looked at 160 individuals who had ulcers. Roughly half of them received this cold balloon treatment. And then half of them received sort of a placebo treatment. They received a balloon treatment, but it wasn't cold. So they filled the balloon with fluid that was room temperature. So they found that with a control group, they actually didn't really have any difference. We can see a slight difference in the percentages between those that experienced relief and those that did not. Now, there's a couple things that make this a better experiment. One is that negative control, people who didn't receive the cold fluid. And also, this is a bigger group. So in the last one, we had 24 individuals. This one, we have 160 individuals. If you have more individuals, it makes your results more credible. So, that group of people, there's a lot of reasons they could have all been shown relief. They could have all had relief because they were expecting relief. This is called the placebo effect, and we'll talk about that in a few minutes. They were all expecting to be relieved, whereas probably these individuals didn't know what to expect. Maybe they didn't even know what treatment they were going to get. And so they didn't have this idea in their head that they would feel better. So this second experiment showed that this refrigerated fluid as treatment for gastric ulcers actually didn't really help. All right, so this placebo effect, this is kind of a baffling and cool idea. So the placebo effect is the idea that someone will respond favorably to any treatment. So basically, this means if you think you're being treated, you're going to be treated. And they don't really know why this happens. It doesn't happen to everybody. But it's sort of like a will. I think of it as like a will to live type thing. Like if you have the will to live, you're going to live. And that's kind of how the placebo effect works. People will think, oh, I don't know if I got echinacea or if I got a sugar pill, but they gave me something, and it could be echinacea, so it's gonna work. I don't know why the placebo effect works. I did a little bit of research, and it doesn't seem like anybody really knows. There's some theories about why it works, but it is an important thing when you're working with humans, because humans have the ability to think about things and to sort of will things to happen. Whether or not they are actually happening, I don't know. But it's really important, and it illustrates the need for a control group, a need for some individuals to not be treated and to not think that they're being treated. Because whether or not this is actually happening is not answering the question of, is this treatment effective? So it's important to consider if you might be having this placebo effect. And even if it's a situation where you're not, say you're working on lab mice or something, they don't know what they're getting. They don't know what you're doing to them. They don't know you're trying to make them better or make them feel worse. But you still need that control group to sort of say, okay, this is what happens when nothing happens, and this is what happens when something happens. And it's just a way to make a better designed experiment. So going along with that, a lot of times you can accidentally introduce bias into an experiment, because people who are answering these questions are usually really passionate about them, and they really want to make people better, or they really want to affect a change for good. And it isn't absolutely not the case that people do this on purpose. Some people might, but they want their experiment to work, and they want to see improvement, and they want to help people. And so there are some things that you can do to ensure that, one, you're not getting the placebo effect, and two, that you're not accidentally introducing bias into your design. So you can do what we call a blind experiment. So this is where your subjects don't know what treatment, if any, they're receiving. So this would be if we looked at our groups 1 and 2 in that echinacea experiment and we said, well, we're not going to tell you if you're getting echinacea or a sugar pill. You're just getting something. So the subjects don't know that they're not getting any treatment. They could have also given that group where they were testing just the duration, they could have also given them sugar pills and just said, you don't know what's going on. You don't know what treatment you're getting. You don't know if and when you're getting echinacea. And so there's sort of no like predisposed idea of what should happen. An even better control is a double-blind experiment. So this is where neither the subjects nor the experimenter know who's treating who. So you introduce a step where the experimenter says, okay, half of my 437 people are going to get echinacea and the other half aren't. Someone else give it to them. So they have no idea which individuals got it. And then the double blind part of this is that the subject doesn't know either. So they don't, the researcher doesn't know who gets the treatment and the subject doesn't know who gets the treatment. So there's got to be some paperwork in here to keep track of actually what's happening. But it's not the experimenter or the subject that knows what's going on. So that is a way to reduce the bias, to reduce the ability of saying, oh, I think I got that treatment, so I know I'm good. And then lastly, we can randomize our subjects. So, oh, there's a mistake in here. Hold on, I'm going to fix this. And just like that, through the magic of technology, we have fixed the slide. All right, so I changed my definition of randomized a little bit. I just apparently copied and pasted something. All right, so in a randomized study, this is a study in which the subjects are randomly assigned to experimental and control groups. So in this way, researchers and subjects have no influence on the composition of the groups. So you can't sort of look at a group and say like, oh, these guys look like they're not doing too bad, and put them into a group, because that's going to skew your results a little bit. If everybody in that group doesn't look too bad, maybe their cold's not quite as severe, but you put them all together and they got all of the same treatment. So if you have a randomized double-blind experimental design, you are doing fantastically. You are reducing sort of any outside subjective analysis of data or subjective results. Now, you don't always have to do a blind or a double-blind experiment. It really depends on what you're doing. If you're working with people, you probably need to do the randomized double-blind. If you're working on lab mice, it's probably a good idea to take steps to ensure that you are not introducing your own biases. So make sure that those mice are randomly separated. Introduce some blinds into your experiment, just so you can't accidentally do any sort of misinterpretation or skewing of results. So once we have done this fantastic randomized double-blind experiment, we're going to collect some data. So this is the stuff of our prediction. There are different types of data that you can collect, and these are really pretty straightforward. You've got quantitative data. So quantitative means numbers, measurements, quantities, things like that. So for example, leaves are 3 inches long. The cold lasted for 4 days. Quantifiable data. We can also have qualitative data. So these are descriptions, non-quantitative values. And there's nothing wrong with qualitative. You just have to keep in mind that they're potentially more subjective depending on how they're measured. So you can't really argue with a correct measurement of a leaf size, or you can't really argue with a correct counting of the duration of a cold. But you could possibly argue with something that's qualitative. So leaves are light green in color and appear wilted. Well, light green to you might be different than light green to me, and depending on the surrounding light green might look different. So you just have to make sure that you're building controls into your experiment so that you sort of get a proper qualitative measurement. An example with the echinacea experiment, people woke feeling rested. Your feeling rested might not be the same as my feeling rested. And so it's not that qualitative values are bad. They absolutely have a place in your experiment. You just have to sort of be careful how you use them, because they could be misinterpreted or not quite interpreted the way you would quantitative. So if at all possible, you want to design your experiment in a way that you get quantitative measurements. All right, so once we get all of this done, we want to display our fantastic data. So we have gone to lengths to ensure that our data collection is going to attempt to answer our specific hypothesis. And then we need to present it in a way that people understand. And you don't want to go through this fantastic experiment and all this work and have people look at your graph and be like, well, I don't know what that's saying. I have no idea what he's talking about. He could be making things up. So you want to attempt to display your data in a way that makes sense. And there are proper ways to display different types of data. And we'll do some of these throughout the semester, so you'll get some practice on this. So we've got bar graphs, line graphs, and pie charts. Those are some of the simplest ways that you can display your data. And you're all probably familiar with these in one sense or another. So a bar graph is usually used for comparisons, whereas a line graph is usually used for trends. So a bar graph might be used to show the number of tornadoes in each month. Whereas a line graph might use to show over several years the number of tornadoes have increased, something like that. A pie chart shows proportions. So when we're doing a graph, there is definitely a way that you need to do them. So the x-axis, the bottom axis, is going to be the independent variable. So the thing that you control, treatment or no treatment. The y-axis is going to show the dependent variable, so the one that changes. So the x-axis might be echinacea treatment or no echinacea treatment. The y-axis might be duration of the cold, how many days the cold lasted. And once you straighten out the independent and the dependent variables, making the graph is the easy part. You just have to keep in mind which variable is the one that's changing. So this graph over here, or this display, sort of shows all of the different important aspects of your graph. So we've got a title. We need to make sure that title describes the content. It can be long, it can be short, as long as it's succinct and actually says what the graph is showing. Then we have the y-axis. So this is the dependent variable. It should be numbered in a way that is makes sense for the data that you have. It should be numbered the same way going all the way up, so regular increments. And then of course, that is our dependent variable. So this is the response to the treatment that you are given. Then we've got our data points. This one is a line graph, so this is showing a trend usually. We've got our x-axis, which is the horizontal one. Again, divided up in a way that makes sense for the data. And then we've got, of course, on the bottom is our independent variable, the one that we are setting. It can be treatments, it can be the times that we take the data measurement. This specific graph is displaying the effect of number of hours studied on performance on a midterm. So if we're looking at number of hours spent, we've got 1, 2, 3, 4, 5. It wouldn't make sense to say, oh, I'm looking at hours spent, so I'm going to mark it in days. No one's studying for days at a time. You might think you are, but you're actually not. You're studying for hours. And so then we've got on the y-axis, the dependent variable, the actual grades that individuals are getting. And so we can look at this and we can see that if you don't spend any time, you don't do as well. This individual spent only 1 hour and did pretty good. But as you increase the number of hours per day that you study on the exam, your grade increases. So here we've got a trend. So take a minute, just look at this, read through this either on the lecture here or in your book. It's got some really good information. All right, so quick review of our independent variables. So an independent variable is the value that you are going to be changing, the thing that you are going to be changing in your experiment. And then, of course, the dependent variable is the result of the independent one. So, for example, on the last slide, we have numbers of hours. The thing that changes is how well a student does on the exam. So dependent is number of hours studied. Independent is, I'm sorry, I said that backwards. Independent is the number of hours studied. Dependent is how well you do on the exam. So in our echinacea experiment, the independent variable was whether or not the individual received treatment, and the dependent variable was the duration or the length of the cold. So we will come back in the next video and actually talk about the conclusion of that echinacea experiment.